Bismillahirrahmanirrahim. The topic for today is the optics of the vision, in which we will be doing the physical principles of optics. So the learning objectives are, by the end of this lecture, you should be able to define reflection and refraction of light, apply refractive principles to lenses, define focal point and focal length, and explain the concept of a reduced eye. Define depth of focus and describe the errors of refraction and their correction, and in the end define visual acuity and different methods of measuring. So now coming to the physical principles of the optics, we know that reflection is the bouncing back of the light when it strikes a smooth surface, and refraction is the bending of the light rays. So this is the difference between the reflection and refraction. So the light, it bends when it goes from one medium to another. It's called as refraction, and the amount of bending, the ratio of the bending, will be measured as refractive index, which is the ratio between the velocity of light in air to the velocity of light in the transparent medium. And this medium can be anything. For example, considering here it's a glass, so the velocity of light in air is 300,000 kilometers per second, divided by the velocity of light in the glass when it passes through the glass, which is about 200,000 kilometers per second, and the refractive index of this glass would be 1.5. Now, refraction at an interface between two media. Refraction only takes place, there are certain rules for refraction to follow whenever there is a difference between the refractive indexes of the two media. For example, the air and the glass we saw in discussed in the previous slide. And the second rule is the interface, it is at an angle to the direction of the light. It is not perpendicular, it is at an angle. And then the magnitude of the refraction depends or is directly proportional to the difference between the refractive indexes of the two media, and then the degree of angulation of the interfaces to the direction of the light. So it is evident here in this diagram. You can see in A, the light waves are traveling, and then there is a glass, but this glass is kept at an angle which is perpendicular to these rays that are traveling. So there is not much difference. The waves, they are usually not bent. They would travel there along their course, the wave fronts. Of course, there would be certain decrease in the velocity and the wavelength, but not much bending occurs. But in the B, you can see if the same glass is kept in an angle, you would see a bending of lights. The bending is far greater and would be earlier here at the ends as compared to the center. Now there are three types of lenses that we'll be discussing here. First of all, the convex lenses, then the concave lenses, and then the cylindrical lenses. So the parallel light rays striking in the center of the lens. Now this is a rule, just make it, if they are perpendicular to the interface, there is no refraction. We saw this, there is no bending. The light rays usually pass straight whenever they are going through the center of the lens. Now this is a rule whether it is a convex lens or whether it is a concave lens. And then towards the periphery, the angulation, since it is angulated, either the sides are thicker or they are leaner, there is an interface difference, so more and more refraction occurs as compared to the center. And then there would be convergence of light when they are bended in case of convex lenses. That's why they are also called as converging lenses. Now, properly formed lens brings all the light rays to a common focal point. A common focal point, what is a focal point? A focal point is a point where all the rays would have to pass. It is a common point. So the convex lens, as we discussed already, they are also called as converging lens because the light rays traveling through them converge, they come together to a common focal point. Here you can see the light rays that are traveling through the center, not much difference occurs because they are perpendicular. Much of the light rays in the center just they go on to a common focal point, whereas those at the edges, at the up and the down, you can see they are usually bending, and when they bend they converge. Convex lenses converge, and this is the focal length, the area, the length behind the convex lens, where the rays they travel a path to a common focal point. This is the focal point where you see all the rays come on together, a common meeting point of all these waves. This is called as a focal point, and this is a focal length, its pathway through which it travels beyond the lens, beyond the convex lens, is called as a focal length. And it travels the focal length and then it comes to a focal point, which is a common meeting point for all these rays. Now concave lenses, the same principle applies. The center of the lens, the light rays, usually they are perpendicular, so there would be no refraction. Light rays usually pass straight. And then peripheral rays, that is the rays at the ends of the lenses, they would be refracted away from the center, that is they are diverging. Concave lens are diverging, the light rays they bend but they diverge. More and more angulation towards the periphery causes more and more refraction, and therefore concave lenses are also called as diverging. Here you can see the rays that are traveling in the center, they just go on like that, they do not bend, but those that are at the ends they bend and they diverge. So these are the physical properties of different concave lenses. Now cylindrical lenses, they bend the light rays on two sides. For example, there is no bending on the top or the bottom, only the side planes are bended. So a focal line is formed instead of a focal point. This is one of the difference from the convex and the concave lenses. There is no focal point, instead there is a focal line, since there is no bending from the top and the bottom. Then we have convex cylindrical lenses. They converge the light rays on one plane only and not the light rays at the right angle to it. And concave cylindrical lenses diverge in one plane and not to the plane at the right angle to it. So if we place two cylindrical lenses of equal strength at right angle to one another, so then we can create a spherical lens of the same length, same strength. Here in this diagram you can see in point A, this is a spherical lens and the light rays are usually traveling it, and then they converge. This is a convex lens, they converge to a common focal point A, denoted by A over here. Whereas you can see this is a cylindrical lens, and in a cylindrical lens you don't have a common focal point, rather you have a focal line, because the light rays from the top and the bottom are not reflected. Only the light rays traveling through the sides are reflected, and so they form a focal line instead of a focal point. So now here again you can see A, this is a line of focus, and this is a cylindrical lens, and you have a point source, and the point source just makes a line focus, since it just would reflect certain light rays from one side and won't from all of the sides of a cylindrical lens. But if we place such cylindrical lens at right angles to one another, if we place two cylindrical lenses at a right angle to one another, then we can make it into a spherical lens. For example, you can see you can form a point focus, and this would act as a convex lens. So because जो वो रेज नहीं रिफ्लेक्ट करे थे एक साइड से, तो ये दूसरा cylindrical lens, by placing it, it would also reflect those rays as well. So you can get a point focus instead of a line focus, which is typical for cylindrical lenses. But if we put two cylindrical lenses at the right angle, we can create a spherical lens, a spherical convex. Now focal length we have already done. What is a focal length? The distance of the focal point for the parallel rays of light. This is the focal point. So जो distance travel करते हैं ये rays to come to a focal point, this distance, then this journey is called as focal length. Now, certain characteristics. Light rays from far point source of light are usually parallel. Light rays from the near point sources are usually diverging. Now, diverging light rays will be focused far behind the focal length. Light rays, for example, they are always moving from center as they enter into the lens. These light rays will not be focused on the focal length. Focal point will be away from the focal length. Now, more powerful lens will be required to focus these light rays at the. This might seem confusing, but you can see it over here in this diagram. Whatever we have read there in that slide. Actually, the problem with recording these videos is most of the time, if I just skip some slides and go through the other slides and come back, all of the recording gets jumbled up. So it's very difficult, but you can just go through that slide, the text of it, and you can correlate here with this diagram. Now, in the uppermost diagram, you can see the light is coming from a distant source. Whenever the light comes from distant source, you can see these are parallel. So the parallel, the light rays, the more focused they are, they pass through the center of the lens. Now, in the second diagram, in the middle one, you can see the light is coming from a point source, and these are diverging. You can see these are diverging rays of light, and when they come, their focal point is usually formed farther away as compared to when the rays are coming parallel. More bending occurs. Now you can change this. For example, if the point source is the same and you increase the power of the lens, you make it more globular, you make it more spherical, and the globular the lens is, the more the refractive power it has, and you can achieve a focal point much closer. Now, formation of the image. All the light rays from a single point source of light in all planes are focused at a common focal point. Every object, of course, is a mosaic of millions of point sources of light, and these point sources are different in intensity, and different in colors, different in different characteristics. And these these sources, they are focused separately. So that's why you perceive them as separate. Now you can see in this diagram you have 2 point sources. One is this one and one is in the bold and one is the dotted one. And both of these different point sources would form different focal points on your retina, and you will be able to identify both of these objects as different points on the retina. Similar formation of the image, you can see the head and the foot. These are the point sources, and you can see the focal point, which is usually formed of this image, which is usually inverted when it passes through the convex lens. But our brain, it is trained to perceive this inverted image as an upright image. So this is the formation of the image by 2 different point sources, and then coordinating them. Now, what is the refractive power of the lens? The degree of the bending of the light rays depends upon different indices. For example, the refractive indices of the two media at an interface and the angulation. The more the angulation, the more the refractive index. The more the difference between the two media, the more the difference of the refractive index between the two media, the more would be the bending of the light rays, and the more would be the diopteric power. So it can be measured by this formula, that is refractive power is equal to 1 divided by the focal length in meters. This can be different for different, you can see lenses. For example, this is a lens with 1 diopteric power, with 2 diopteric power, and then this one is with 10 diopteric power. The greater the power, the more the focus. Now the refractive power of the concave lens, since concave lenses are diverging lenses, so you cannot come up with a focal point. How can we measure the refractive power of a concave lens then? We can do that by comparing it with the convex lenses, as convex lenses converge light. So if these two exactly neutralize the reflection of each other, they have equal but opposite refractive power. So by calculating the power of the convex lens and then comparing it to the concave, we can find out the power of the concave lens by comparability to the convex lens. The concave lens refractive power is usually expressed with a negative sign, for example, -1. Now there are four interfaces of the lens system and different refractive indexes. You can see over here when we are considering our eye, it just works like a camera. For example, you have a lens system, you have a pupil aperture to allow amount of light entering into your eye, and then you have certain accommodation powers, and then it has to pass through a lens system, and then the image finally is formed that is corresponds to the film, for example, of a camera. So now you must know what are the different interfaces and what are the different refractive indexes of all these. For example, air is 1, cornea is 1.38, 1.33 aqueous humor, lens and vitreous humor. You must memorize these refractive indices of. Now reduced eye is very important. If we add up all of these indices, these refractive indices, so we can calculate, we can have an eye which is called as a reduced eye, and the total refractive power of this reduced eye is 59 diopters. Now how can we do that? For example, and you have an object, and this is the pathway. The first interface is between the air and the anterior surface of the cornea. This is your first interface. The second interface is between the posterior surface of the cornea and the aqueous humor. The third interface is between the anterior surface of the lens and the aqueous humor, and the fourth interface is between the posterior surface of the lens and the vitreous humor. The image usually forms right on spot on the retina. So these are the four interfaces through which the light rays they are passing, and they have to pass through it. And if we calculate all of them, and we can then it is called as a reduced eye. If we add up all of these refractive. Now the lens system of the eye, as we just went through it, the refractive power is about total of 59 diopters, and maximum refraction that usually occurs at the cornea. Why? As we might have thought, as you guys might have thought, that the refraction occurs, maximum refraction would be occurring at the lens, but no. It is the cornea, because the cornea, the refractive indices of the air and the cornea, there is a maximum difference between them. And as a rule, we said that the greater the difference between the refractive indices, the greater would be the refraction, and the greater the maximum angulation at the interface. The refractive power of the lens is only 20 diopters as compared to the 40 diopters, which is because of the cornea. But still then the lens contributes 20 diopters, but it is important in providing accommodation for different distances of objects from the eye, because it has neural control. If you remember your topic from the parasympathetic nervous system, the third nerve, it is supplying your all of this eye system by which you can accommodate, you can increase the power of the lens, or you can just relax. And this is done through your parasympathetic nervous system. So the lens at time can increase its diopteric power far greater than the cornea contributes. So what is accommodation? The parallel light rays from far objects are focused on the retina. By 59 diopter of power of the lens system, we already did that if we consider all of that as a lens system. So 59 diopters it contributes to it. Light rays from near objects are usually diverging, and diverging light rays require more powerful lens to focus at the retina. Refractive power of the lens, usually this lens is crystalline. When you are young, it has protein made up of protein substances, which is your crystalline, which is clear, and you can adapt, for you can increase your diopteric power from 20 diopters for example to 34, that is 14 diopters. You can increase your accommodation power. But as you age and as your lens becomes worn out, all the protein is being used up, it becomes cloggy and it becomes opaque, so your lens loses its accommodation power. But as you are young, for example, a child may be having a greater diopteric accommodation power as compared to a young adult, and a young adult has a greater accommodation power as compared to an old individual. So 14 diopteric increase you can have in your. Now, how does this accommodation occurs? It is because of the suspensory ligaments that usually are surrounded. There are more than 70 of them. They are surrounding your lens and controlling the tense lens, the shape of the lens. And then you have the ciliary muscle adjoining it, and these ciliary muscles have two types of fibers, that is meridional fibers and the circular fibers. It has intense parasympathetic stimulation and which usually innervates the ciliary muscle. And in time, for example, you want to increase your accommodation power, there would be a contraction of these meridional and the circular fibers, and the contraction of these would always release the tension from the suspensory ligament, and they are going to make your lens more spherical and more for accommodation, more accommodating power for. Now, presbyopia, normal accommodation power is 14 diopters, but with advancing age, there is denaturation of the lens proteins. For example, the proteins, they form a coagulum, they become opaque instead of being fluid-like, they become opaque, they become much more like denatured, and there is so whenever they are denatured, the lens, it would become more stone like of a consistency, it would lose its elasticity. So once the elasticity is lost, then it cannot change its curvature, it cannot become more globular, more spherical. Accommodation power is lost, and the lens has then only just fixed refractive power. So this is called as presbyopia with age. This is a normal phenomena that occurs. You lose your accommodation power, and this is usually corrected by the bifocal lenses, which corrects for both the near vision and the far vision. For example, the far vision would you will be looking through the lenses would have division. The upper part you can see for your far vision, and the lower part you can see for your near vision. For example, you are reading something. So we only have minus for concave lenses, and we always have plus for convex lenses, which are used for near vision and far vision. Now, there are errors of refraction. Emetropia is not an error of refraction. Emetropia refers to the normal refractive power of the eye. Though the errors of refraction are called as myopia, which is also called as nearsightedness. You can see near objects quite easily, but not the far objects. And hypermetropia, in which you can see the far objects quite clearly, but not the near objects. And there are certain physiological and physical properties of why these occur. For example, myopia, the lens system is stronger. The lens system is very strong as compared to the normal eye, or the eyeball is more elongated. So the parallel rays of light usually are focused in front of the retina, not on the retina. In emetropia normal condition, we want the light rays to be focused on the retina. So if they are focused in front of the retina, मतलब कि वो focus बहुत जल्दी हो जाते हैं because of a stronger eyeball system, because of a stronger lens system, sorry, or an eyeball that is too long, too elongated. Then you have myopia, which is also called as nearsightedness. Now, the farsightedness or hypermetropia, in this, the lens system is so weak, or the eyeball may be so short that the parallel rays of light are focused usually behind the retina. Now you can see here in the diagram, this is emetropia. The focus is right on the retina. This is hyperopia or hypermetropia, farsightedness. We did this because we said that either the lens system is so weak or the eyeball is so small enough, so the parallel light rays usually they are focusing far behind the retina. In myopia, you have the lens system either so strong or the eyeball too oblong or long that the parallel rays of light usually they get focused in front of the retina. This is called as myopia or nearsightedness. So myopia, some characteristics of it, refractive power is more, parallel rays of light are focused in front of retina. A person cannot see the far objects. Some of the refractive power has to be neutralized by concave lenses. We will see that now just by a diagram how we can correct this refractive power. So the correction of myopia is with the concave. Now hypermetropia, that is far-sightedness, refractive power is less. The parallel light rays are focused behind the retina, and the person uses, you can see the far objects clearly, and the for near objects has to use accommodation. You cannot see the nearer objects even after using the full power of accommodation. So you can see here in this diagram, this is that we will use for myopia, where the images are focused in front of the retina. We want to dissipate some of the power of this lens system, so we just correct it by using a concave lens which diverges light rays and would decrease some of the power at least of the so stronger lens system here which is present in myopics, so that you can see in this dotted lines, by using the concave lens the image is formed right on the retina. And this is the case of hypermetropia or farsightedness. This is because of a lens system that is too weak, so we'd use a spherical convex lens which we know that converges light and therefore would give strength to the lens system. And by the dotted line you can see the image is formed right on the retina and not beyond the retina at the back. Now astigmatism. Astigmatism is when the light is usually focused from certain aspects and left from certain aspects. For example, we usually treat astigmatism by using cylindrical lenses. For example, we can usually use two cylindrical lenses that are put usually at right angle to the lens system of the eye, and in this way we can get a focal point. Now, for finding the axis of the abnormal cylinder, or a parallel black bar chart is usually used for determining astigmatism. I told you that astigmatism is also an error of refraction in which the light is focused from certain aspect but is not focused, for example, from certain from those at the right angle. And for correction of astigmatism, we use two cylindrical lenses that are put at the right angle to one another. So in this we can usually then get a point focus. You can see here a point focus. This is the parallel black bar chart. Now you can see this is for determining several methods usually exist for determining the axis of abnormal cylindrical component of the lens system of the eye. This is one of them. And you can see some bars over here are vertical, some are horizontal, and some are at varying angles to these horizontal and vertical bars. And we can once we find out the axis, for example, at which axis there is the void, the examiner then tries for example with the positive cylindrical lenses and the negative cylindrical lenses which are placed, and we find out a focus point for a person then who would be able to see all these bars, not just only the 9, the 3, the 2, the 1, which would be abnormal. So we are going to place different lenses, and we are going to find out a point where the person would be able to see all these bars, and this would be the point of focus, because astigmatism causes the visual image in one plane to focus at a different distance from that at the plane of at a right angle. So this can be because if, for example, the curvature of the cornea in one plane is greater than another, an abnormal condition, for example. And there is an example in your guidance which tells that, for example, astigmatic lens would be seen like, for example, you put an egg lying sideways to the incoming light rays. The degree of curvature in one plane through the long axis of the egg would not be as great as the curvature through the short axis. So this is what basically the physiology is, and for astigmatic lens we have to usually correct them with cylindrical lenses, and we take the help of this a lot of methods, but the most common one used is the parallel black bar chart. Now, pupillary aperture is very important in the focusing of light and the control. It controls the amount of light. For example, in the daytime, you don't want a lot of light to enter, so it would be constricting, and at nighttime, where you want a lot of light, so it would be dilating, and basically it controls the amount of light. So the diameter of the pupil is 1.5 to 8 mm. The amount of light is proportional to the square of the diameter, and the amount of light can vary, that is about 30 times. And one of the important aspect that I took up the pupillary aperture is the depth of focus, its effect on the depth of focus. Constricted pupil, whenever your pupil is constricted, okay, it increases the depth of focus. It would increase the image, the focus of the image, whatever you are looking at, and it would not change it much even if you move your eyes here and there, or you move your head, for example, or you move forward or backward. All light rays pass almost through the center of the lens. Because you have constricted pupils, so the light rays usually are traveling are parallel, and they cross your center, and the center you have fovea centralis, and the maximum you have vision over there. Central light rays are always better focused, and it is the same principle as you have a pinhole camera in. Now you can see here in this diagram the upper one and the lower one. The only difference between this is that the upper one, the pupil is constricted, the lower one, the pupil is dilated. A lot of light is entering. Now you can see in the this image, the light entering with a constricted pupil usually goes through the center of the lens. It has a very sharp focus, and if you move on the retina, and if you move your retina forward or backward, shown here by the black dotted lines, you see not much effect is present on the focal point. There is no blurring. The focal point still remains same. So the more your pupil is constricted, the more sharper the focus, the more clearer the picture, and even if you move your retina backward and forward, no much change would be there on the focal point. But coming here to an enlarge or in the Dilated pupil, a lot of light is entering through the lens going here and there, though you get the same focal point at the retina, but you can see through these black dotted lines, if you move your retina forward or backward, there's intense blurring of the focal point both forwards and backwards. And so it summarizes that the smaller the pupil, the sharper the focal point, and the more you move, still the focal point remains the same. The dilated the pupil, the more the light enters, the focal point does form on the retina, but with movement, you are going to get a great blur of the image formed. Now, another important topic is visual acuity from your practical point of view. What is visual acuity? How do you measure it? What are different tests for it, for measuring it? This is a very important practical aspect, but here I would just shortly describe definition. What is visual acuity? Sharpness of vision. Now, sharpness of vision, as you have most of you would have an eye test. You go to an ophthalmologist and there is that Snellen's chart hanging on the wall, and you have to tell out or read out the numerals, or either its alphabets or either its pictures, and then you can tell the different alphabets from a particular distance, and you can tell them apart. That is 2-point discrimination. You can tell 2 points apart and sharply. This is called as visual acuity. So the 2-point sources of light usually discriminated if the focal points on the retina are 2 mm away from one another. So then only you can tell these 2-point sources to be different. So in central retina, you have maximum visual acuity. And in the peripheral retina, the visual acuity is usually decreased. So you can see if the 2-point sources on the retina are 2 mm apart, then you can probably tell these two objects different, and this is the visual acuity, that is sharpness. And you can determine visual acuity by different ways. For example, there's Snellen chart, there's Jagger's chart for near vision, for far vision. You have different methods to measure it. Now, determination of distance. So how your eye can determine the distance of object from the eyes. These are by 3 methods. The size of the image of known object. For example, you know the size of an object, so your mind can automatically calculate the distance of the object from you. The phenomena of moving parallax and the phenomena of stereopsis. So we are going to do one. First of all, size of the image. Now, image of the far object is smaller, of course, than the nearer object. And then the brain knows the size of the image of the known object when they appear near and change in size when the object is far away. For example, you know there is a 6 feet tall adult standing in front of you. You know the size of the object, so your brain automatically calculates the distance from this. Now, phenomena of moving parallax. Images of nearer objects moves more across the retina with the movement of the eye. So the very near the objects are out of field of vision with small movements of the eyes or the head. The movements that are far away usually does not change. For example, you are looking at 2 objects, one is near and one is in your far field of vision, and you start moving your head or your eyes. So the nearer object would get blurred, but there would be no change on the far object which is in your field of vision. Far object's image remains on the retina even with tremendous movement of the eye of the head. From this phenomena, brain estimates the distance of the objects, and this can also be done through single eye. You don't need both the eyes for this. For example, you are looking to one of your friend who is sitting beside you. and then you have somebody standing quite far away from it. The moment you move, so the image of your friend sitting nearby is going to go out of the field of the vision with very small movement of the eyes. However, the image of your friend standing far away, not much would be affected. And you can get this, you can measure this distance through one eye as well. Both eyes are not necessary at a time for measuring the phenomena of moving. Phenomena of stereopsis, it is called as binocular. You need both eyes for stereopsis to measure. Objects which are usually very near to your eyes form images on the temporal side of the retina, and those objects that move away from the eyes, they come more towards the nasal side of your retina. So nearer objects have more unfused points of the two images than the far objects. And so from these two phenomena, from the known and the unknown, you can estimate the distance. You can see this by the diagram over here. You have a red circle, which is an object of known distance and size, and it is nearer to your eye. So you can see it is forming an image on the temporal side of your retina. And then you have an object far away of an unknown size, which you can see here as a yellow square, and it is usually going to form an image more nasally, more medially on the retina. Okay, so that was the end of our lecture, and the consecutive 3 slide is the result of whatever assignments I gave you guys. Please go through these, each one of you, and if somebody's result is missing, there's nothing to panic. You can write to me. I will re-look into it. Actually, the compiling result was so a tremendous job, because everybody sent me so many files, and then going through each one of the file, I just was totally confused with compiling this result. In the next time, I don't want anybody mailing me the assignment 5 times or 6 times. It makes it quite difficult for me. So please go through these results and be serious with whatever assignments are given to you, because it is going to count in the end. And we don't want you guys to suffer. You guys are already suffering a lot. All of us are suffering. But still, Osama Khan, I got none of your assignment. So you get a 000 over here, a triple bond. Then I have Samiur Rahman with a triple bond, and a Alina Khan with a 000, and then a Khalid Hamid Khan with a 000. Please kindly go. If you guys had sent me an assignment, please do. If I'm wrong, I will just correct up the results. But these are the results which I have compiled repeatedly after going through them, and these are the finalized. These are still not finalized. I'm just still going here and there, and any one of you who have given me all the 3 assignments and I have not marked, please feel to talk through your class representative or your girls through your GR. So please go. And then I have Hamza Rahman. Please, I'm announcing these names. Amjad Khan, who have given me no assignment, with a total 0 for their internal assessment. Your internal assessment be 40 marks. Please be reminded, even greater than anticipated, and even they might increase the weightage. So sitting for you at home, I know things are quite difficult, but you can easily do assignment, write assignment, and send it to us. Whosoever is giving you these assignments. I hope all of you are doing well, and I pray for your safety, and see you next time, inshallah.